A very good evening and a very warm welcome to one and all present here. Today we have with us our speaker, Dr. Navin Kumar Rastogi. So Dr. Rastogi is a chief scientist and head at the Department of Food Engineering at the CSIR Central Food Technological Research Institute in Mysore. Before completing his PhD in food engineering, Dr. Rastogi completed his BTech in Chemical Technology and Food Technology as a gold medalist with Merit Scholarship and his MBA in Marketing and Personnel Management and MTech in Engineering Management, both as a first rank holder. Dr. Rastogi has several professional awards to his credit. This includes AFST Young Scientist Award in 2000, CSIR Young Scientist Award in 2001, AFST Lalji Budu Nidhi Smarak Award in 2003, CFTRI Award in the category of Best Technology Transfer to Industry for Production of Virgin Coconut Oil by Wet Processing. Dr. Rastogi is a recipient of the Seligan APV Fellowship by Society of Chemical Industry, London. He's also a recipient of the DAAD Fellowship by the German Academic Exchange Service. He's also a fellow of DBT Overseas Fellowship, AFSTI, National Academy of Agricultural Sciences, Institution of Engineers, Indian National Academy of Engineering, and National Academy of Science. Dr. Rastogi is the author of 170 publications with an H index of 50. He has also been involved in significant foreign assignments in University of Reading in UK, Berlin University of Technology, Germany, and Ohio State University in the US. With this introduction, I would now like to call Dr. Rastogi sir for his presentation. And also, I would like to request all the participants to kindly mute their mics and also their videos. Thank you, sir.
I'm trying to share. Thank you very much for the nice introduction. And I don't know why sharing mode is. Whether slides are visible? Okay. So very good afternoon, good evening to the students, mentors, and the faculties from the different institutions, India and abroad. I have chosen the topic today on the opportunities and challenges in the novel application of membrane in food processing. So we'll begin with this. I'll just start with the beginning, like what are the different membranes, how the membrane processing came into practice in India, abroad, and what are the different applications, and what are the limitations of the membrane processing, and how can we solve this. And just for your information, we can tell you that India is in forefront in developing the many membrane-based processes and the membranes as well. and it has achieved a landmark of concentrating right from the very low concentration to the very high concentration. And most of the work reported have come from the India and about the natural colorants and the fruit juices. And some of those work have been done in our group. And I thank Dr. Mishra for giving me this opportunity to present my work. So if we'll just begin with that, how membrane processing started. Like we had initially we had only 3 membrane processing, like reverse osmosis, ultrafiltration. Hello, can you hear?
They are not moving. PPTs are not moving.
Is that moving?
Presentation is not moving.
Is that moving now?
No. I don't think. Yes, now it is fine. But you go to please presentation mode, PPT mode.
Is that all right, sir?
नहीं अभी PPT मोड में जाओ जरा अभी भी फुल स्क्रीन नहीं है प्रेजेंटेशन मोड में नहीं है मूव तो हो रहा है लेकिन प्रेजेंटेशन मोड में नहीं है
सर प्लीज अगेन शेयर योर
ओके but we are seeing only the
entire इनके लिंक entire स्क्रीन क्लियर करो अभी भी नहीं दिख रहा है
now it is fine sir you can go to your presentation mode.
Yes. Is that fine?
Yes sir.
Yes.
Hello?
Now it's fine. Now it is fine.
Okay, sir. So we just restart with that, and we'll say that India is in the forefront in the developing the membrane processing technology, and a lot of the work has been reported come from the India from different laboratories, and for the further there are limitations in the membrane processing, and I'll be discussing now. And initially when the membrane processing started, it started with the reverse osmosis, ultrafiltration, and the microfiltration. So reverse osmosis, we all see that reverse osmosis is being used for the purification of domestic water purification nowadays in India. Because with the advent of the many of the membrane processing industries, they have come to India, and they have launched several membrane processing units, like RO units are available in India, and it has replaced the UV or any other processing steps for the water purification. And another operation is the microfiltration and the ultrafiltration. It is only used for the clarification, where RO only we use for the concentration or the purification of the water. How it started, it's not very far like that. We started this membrane processing is only in 1950 to 1960, where the RO and UF emerged with the practical flux. What was happening earlier, those membranes were used, either the membranes were used from the leather or from the skin of the animals, but the flux was the problem. Like it was not having a significant flux. That's why membranes were not able to use in anywhere in the chemical or the food processing industries. But at the end of the 1970s, it was developed like a cross-flow filtration techniques were developed, which led to the manufacture of the commercial membrane systems. Earlier, it was not used because of the low flux. Now, when we had the higher flux, then the membrane we started using membranes in many of the chemical processing. And membrane acts as a selective permeable barrier to separate one or more solutes in liquid. If we date back the history of the membranes, it was very long back, actually, maybe 1,000 years before the membranes were used. But those membranes were not the commercial membranes or not the manufactured or synthetic membrane. The people were using the membranes from either the animal skins and for the concentration. And if you look at this, just for the illustration, all of us know about this, how we define the reverse osmosis or the ultrafiltration. Reverse osmosis rejects the salts and passes the water. And in case of ultrafiltration removes the protein, and salts and water can pass through. So it leads to the fractionation and partial purification. Whereas membrane, in the RO membrane, leads to the purification of the water. And that's what now we are in the, every household is almost having a RO purification system. And even the government and the private companies have put up a membrane processing system where we can collect drinking water at a very cheaper rate, and that is also membrane processed water. So what are the advantages of membrane concentration over the concentration by evaporation? We can concentrate any food product or any in the chemical processing industries by evaporation is very well known, where we have to supply the heat and water gets heated, and there is a change of the phase takes place, and it requires energy here. So here the lot of energy is required for the evaporation here. But in case of membranes, we are not encountering any phase change. So that's why it is called as a very low energy consumption process, because there is no phase change, and when it is not heated, so there is a less aroma and flavor retention is very high. And because we don't need a boiler for any heating or anything here, so it reduces the cost, capital equipment cost, and we are working at the low temperature and low pressure process. So we don't require a very high machining or very high costly equipments, because it is a low temperature and ambient temperature processing, or maybe at low temperature in case of microfiltration, ultrafiltration, or reverse osmosis. And there is no thermal damage, because I've just discussed about it, because we are dealing at an ambient temperature. So there is no thermal damage. If there is no thermal damage, we have a better food product quality. And then the cost of the processing, it will reduce, and it will give us a ease of operation, because it is the scaling up and all these aspects are very easy in the membrane. So unlike the evaporation, like we need to, if we want to increase the capacity of evaporation, we need to buy an evaporator, make a calculation. Here we can just keep on adding the modules, and we can increase the capacity of the plant. And it has a very vital role in the separation processes. Maybe I'll just give you a few examples whether you will realize that how the membrane are being used in the food processing. But before that, all that glitters are not gold. So look at this. What are the limitations? Limitation is still we consider that we need to have a very high flux membranes. So there is a little bit improvement is required in the membrane flux, and there is a limited concentration. If you look at the microfiltration, ultrafiltration, and reverse osmosis can concentrate a product only up to 25-degree Brix. The reason being is that it requires a very high pressure after that concentration, 25-degree Brix, and we don't have to have a membrane or reverse osmosis membranes which can withstand such pressure. And then another thing is that sometimes it requires a capital cost, because earlier, this is the earlier scenario when India was not able to manufacture the membrane. Now several companies have come in India and making the membranes, and there are the temperature and the concentration polarizations are the necessary evil of the membrane, and we need to deal with it. We need to have a strategy to reduce the concentration polarization. I have discussed this thing in my talk, like what is the concentration polarization, fouling of the membranes, and when we can use those membranes for years together. But only thing is that if membrane fouls, we need to stop the operation, clean it here, put it back. But there are two things like concentration polarization and membrane fouling. These two things, concentration polarization is a reversible process. Like when we can stop this, and we have several strategies to reverse the concentration polarization. But in case of membrane fouling, once the membrane fouls, we cannot repair it again, and it has to be discarded. We have to change it. How the fouling is taking place is that the membrane are it's like a lipid film, and where there are the film, there are the pores here. Those pores get filled up with either the impurities or the proteins, and it becomes, we cannot operate with the membrane anymore because the flux reduces, and then we need to change the membrane. But this does not happen very often. It may happen only in the 1 to 2 years for the polymeric membranes, or maybe 5 to 7 years for the ceramic membranes. But membranes have a very long life, and it requires the rigorous cleaning procedures. These are the necessary evils. If we are using the membranes, we need to encounter these, and we need to have a strategy. How can we do this? And you may be hearing that people are using the membranes even in the milk processing for the concentration of the milk, because milk has to be concentrated for the spray drying or any condensed milk, and that requires a lot of energy for removing the water, and the quality also gets impaired. If we use the membrane, the quality of the milk will be much better, and at a cheaper rate we can remove the heat from the milk. And there are fruit juices, heat sensitive fruit juices, colorants, natural colorants. We can use the membranes in many other operations. I was just telling you, the membrane can be used, reverse osmosis membranes can be used only up to 25 degree Brix concentration. The reason is here, the most of the fruit juices have 75 to 90% water, 9 to 25% sugar, means in general, some organic acids, dietary fiber, proteins, and this can give us a very high osmotic pressure. It is in the range of 6 to 10 into 10 power 5 Pascal, and it need a very high applied pressure. Like we need to apply very high pressure at the time of the reverse osmosis. And some of the membranes, like we need to fabricate the membranes which should withstand that pressure, and that is going to be expensive. And when we make the membranes thicker, then it reduces the mass transfer. When it reduces the mass transfer, then the rate of the flux will be low. So that's why we can concentrate the fruit juices by using reverse osmosis only up to 25 degree Brix, around close to that. And just for example, if you look at this sucrose, 1% sucrose will have like atmospheric pressure, 1 psi. Orange juice 10%, what is the single strength orange juice comes out around 10%, will have 210 atmospheric pressure. We need to apply this much of the pressure to concentrate this. So, and once it gets concentrated to 42%, it has a very high pressure, ranging to 1400 around psi here. So again, if the concentration increases, we need to increase the pressure applied, and the pressure applied increases means it increases everything, cost of the membrane, cost of the equipment. So there is a limitation in the use in the reverse osmosis. But I was keep on telling here, reverse osmosis have hit the market, and it has hit the domestic market for the purification of the water. There is no concentration, only we are purifying the water, removing all the impurities, maybe TDS, and it's found to be very good because we don't require a very high flow rate for that or very big pump. So a small pump and a small membrane like ion exchange, and there are several companies have put up their plants in India. That's why membrane processing, like water plants, have become very cheaper. And it depends upon the retention of the solute, depends upon the solubility and diffusivity. Maybe I'll just taking up this further, how the membrane transfers the water. The water first solubilizes in the membrane material, and then it diffuses on the other side. So it depends upon these two properties, solubility and the diffusivity. And RO, rate of rejection has to be 100%. But if you look at this, we are looking for the mineral water, and if we are removing 100% minerals, then water will become a plain water. So some of the membranes, RO membranes, have been made in such a way that it can only remove 95% of the minerals. Rest 5% of the minerals are required for our health. Some of the membrane manufacturers have come with 100% rejection. So they are not very good for our health because we need minimum minerals for the body. So at least 90 to 95% of the minerals have to be retained in the water. And if we talk about the ultrafiltration, it removes the higher molecular weight compounds. Like this can be used for the concentration, clarification, concentration of the enzymes. We are using ultrafiltration, and for the clarification of the fruit juices can be used, and rejection can be 95 to 100%. What are the factors which affect the performance? Like here, like molecular weights and the concentration. Low molecular weight compounds and the water pass through the membrane. If it is like a membrane, some membranes will pass, only the water will pass through, and low molecular weight compounds, whereas the large molecular weight compounds will be retained on the surface. It is typical in case of the ultrafiltration membrane as well as for the RO membranes, where only the maximum water is passing through. Ultrafiltration membrane's pore size is very large, like it can withhold, it can stop the enzymes, it can stop the proteins, and it can even fractionate between the two proteins having the different molecular weights. So these membranes are very useful for the fractionation, and then solute concentration in the bulk is inversely proportional, like whatever the concentration the solute is there it is inversely proportional. And if you have very high viscosity of the feed, and it leads to the formation of the polymer gel at the membrane, that reduces the mass transfer. So viscosity of the feed should not be very high. Suppose we are filtering a mango pulp here, mango has a very high viscosity. So our strategy should be to reduce the viscosity of the mango by using either the pectinase and cellulose enzyme, and then we can filter it. We can separate the serum and the other compounds from the mango, and serum can be concentrated and we can make a different products out of it. Another point is that velocity, like if we need to circulate the liquid at a very high speed across that transmembrane or transitional velocity should be very high, because it leads to the higher Reynolds number. If the Reynolds number is higher, the mass transfer will be higher, and the formation of the polymer gel layer can be reduced, and it will give us a better performance. Another factor is the high temperature increases the osmotic pressure. It is always good for us, but only thing is that in case of natural colorants and the heat sensitive fruit juices, we cannot increase the temperature more than 40 or 45 degree. So chemical plant, we can, of course, we can increase the temperature and get the higher flux. But in food processing, we are more concerned about the organoleptic properties. So we cannot increase the temperature for the natural colorants more than 40. Or the fruit juices also cannot be very high. But at the moderate temperatures can give us a higher flux. So these are some of the factors which we need to consider when that affects the performance of the membrane. Let us come to the concentration polarization. This is, as I earlier discussed, it is a necessary evil. Whenever membrane is there, concentration polarization is in place. So if you consider this as a white portion is the membrane, and in between there are pores here, what will happen? Here suppose red side is the highly concentrated liquid, and when it passes through it, what happens here? Whatever the molecules is lower than this size will pass through. What will happen? The molecular weight having the molecules having higher molecular weight will get concentrated on the surface of the membrane. And if something is accumulating on the surface of the membrane, it will give us a build-up of the retained concentration. When the built-up concentration increases, flux decreases. And in all the cases, we want to have a higher flux because our process has to be faster. And this is not a serious problem for us. This is a problem, but not as very serious, because we consider it as a reversible phenomena. There are methods. We can disturb this layer, we can reverse this layer, we can apply some kind of a physical effects. It can disturb the layer. But more problem will be there if we do not address the concentration polarization, and these pores are being blocked by either the proteins or the impurities. Then we can never clean those pores, and then what will happen here? These membranes will get permanently damaged. We cannot use those membranes. So it gives us an alarming situation for us. Like when the concentration polarization takes place, we need to be alert, and we can reverse it, and then we can put it back to the system again. And then if fouling occurs, no way we can reverse the membrane, and because proteins will be absorbed on the surface, plugging of the pores, and number of the phenomena will take place. Like gel layer is formed and long-term decline in the flux. We can, even if you wash it with the hydrochloric acid or something, it may damage the membrane, it may damage the pores, but it will not be reversible. So we need, at that situation, we need to change the membranes. How can we improve the flux? That is another question, like generally comes here. If the concentration polarization occurs, what shall we do here? How do we increase the flux here? Best thing is that stop the process, and the constant and fouling should be then we can reduce the fouling. And other ways, like we can induce the turbulence promotion. There are several ways to induce the turbulence, like we can even use the ultrasound, and we can reverse the flux, reverse the flow, and we can do many things, and we disturb the flow so that, and maybe we can take out the membrane, wash it, put it back again, and then there are like back flushing is that we can reverse the direction of the flow, washing and first flow here. These things will reverse the concentration polarization, but it should have been done before the fouling occurs. Another thing here, this is also very necessary evil here. The membranes, when we are using, we cannot keep it just like that here, because it requires a very rigorous cleaning procedures. And because how do we check the adequacy of the membrane even after the several cycles? Like we can check the flux. There is no way to check whether the membranes has become like a original membrane. What we can do is we can check the flux. Suppose it is a, generally we measure in LMH. If it is a 20 LMH and after cleaning it becomes 20 LMH, means it is cleaned. If it is less than that, we need to clean it further. Maybe for cleaning, we can use a variety of the acid, alkali, detergents, sanitizers, and combination of those we can use. And and we can de-stress the foulants accumulated on the membrane system. And maybe just I like to highlight here, whatever that here the detergents and soaps available in the market, like whatever the foreign detergents are, all are making the detergents for the membrane cleaning, and then can be used for the cleaning of the membrane. Very mild to the very hard detergents are there. Maybe non-enzymatic based to the enzymatic based detergents are also available in the market for cleaning the membranes. And generally we would like to have a CIP system, clean in place system for the membrane. That would have been the best. But what we can do is, suppose we are working with the apple juice concentration, we can apply the CIP system at, we can circulate the water or this at 50 degrees centigrade. It will have a CIP effect. Or we can use some kind of alkali detergent with 100 to 1000 ppm free chlorine free based system we can use. It will clean the membrane. So generally we need to devise a cleaning procedure for our applications. What are our applications? If it is a chemical based process, we do not have to worry, because we have lot of detergents, mild to the hard detergents cleaning, we can do it. But if it is for the food processing, we need to be very careful, because this alkali and acid should not be a part of the food in later cycles. So it has to be cleaned, and we have to ascertain number of times whether the membrane has been cleaned. If the flux is not restored, we need to do it again and again. So just maybe a part of theory about the membrane, like suppose this is the tubular membrane. If it is, the liquid is flowing through the membrane, this is the feed pressure, this is the retentate pressure, there is a pressure drop, and whatever the pressure coming out here, permeate is coming out. If we look at, we can calculate the delta P from this. Delta P is feed pressure plus retentate pressure by 2, because we take the average of this pressure, minus the PF is the permeate pressure, and that tells us about the delta P. And this is a very regular equation, general equation we use to calculate the flux. Flux is like K into A is the membrane area, delta P the way we have calculated, minus delta pi is the difference in the osmotic pressures. Since we are dealing with the large molecules in the reverse osmosis, the delta pi may not be very significant. Maybe we'll take up the novel membrane processing systems where delta P will not be significant, but delta pi will play all the role. So there are different mechanisms given for the membrane processing. So it looks like that there are pores and the porous membrane is passing through it. But it is not happening like this. It is something like that. When the membrane, when it is taking place, when the liquid is coming inside, it will first get dissolved in the membrane material, and when it get dissolved, so that's why we called as a solubility. The membrane, the solvent should be first soluble. When it becomes soluble, then it diffuses out. So that's why these two physical properties, solubility and diffusivity, are very important in the membrane processing. So that's why the first theory has come based on that solution diffusion theory. Another vapor pressure theory, molecular sieving. Molecular sieving is like, people say it is like a sieve here, the size, and whatever the size it is passing through. May be true for the ultrafiltration type of membranes, I'm not sure, but molecular sieving means there are different school of thoughts. And preferential sorption, like if you have two materials, one material can be sorbed on the surface, other will just pass through, and then it is sorbed, then it will pass through the other side to the permeate side. Another is like hydrogen bonding. When the material is passing through this, it will get bind with the hydrogen, and when it because of the hydrogen binding, it binds and then it passes to the permeate side. These are the different school of thoughts. And so what are those membranes made up of? Like it comes to the question here, what is this magic material made up of? And like that, if you look at this, it is just nothing but a polymer. It doesn't look very different, like just like a plastic bag or something like that, plastic material. If you look at the cellulose acetate, is a very common membrane material. It is being used, but the problem is that its durability is not very high. So then polyamide, polysulfone, these are also polymers, but have a higher durability. These are the synthetic polymers. And the later inorganic membranes material like aluminum oxide, zirconium oxide, ceramics, and carbon fibers. Lot of things have been introduced in making for use of the membrane here. And if you look at this, polymeric membranes, they do not have a very high life. So it may be for 1 to 2 years. But whereas if we have a ceramic membrane, it will have a life up to 6 to 7 years, continuous use. And it can work at any pH, 0 to 14. And and this is the advent here when what happened in 1970 when asymmetric membranes were introduced in the world. And like asymmetric membranes, it will have a membrane will be very thin, but it is supported by a open structure. Open structure offers a very high mass transfer resistance. And this overall mass transfer resistance, if you see, membranes will have a very high mass transfer resistance, which requires a very high pressure application. So that's why the efforts are made to reduce the thickness of the support material. If we reduce the thickness of the support material, membranes will become vulnerable to the pressure. So there is a compromise between them, whether the skin, only the thin skin acts as a membrane, but support layer has to be there to make it strong. So how do we select the membrane here? Like it is based on the pressure. What is the pressure requirement? What is the temperature requirement? What is the pH of the system? Whether the food, what is the chemical compatibility of the membrane? And now another thing is that for the food uses, we have to be very careful whether it is approved for the food use and it is durable, availability in India or maybe continuous supply is assured, and the cost has to be less. Because if you look at any of the membrane processing plant, the cost of the membrane is very high earlier because we were importing the membranes. Now in India we are making the membranes. That's why it is being used in many operations. And even many of the water purification plants all over the world are based on the membranes. Earlier most of the plants were based on the evaporation and evaporating the seawater, recovery the salt and like, but now most of the plants are based on the membranes, RO membranes. And as I just discussed, polymembrane membranes have a very short life, like 1 year, because continuously you can use for 1 year. But if you use ceramic membranes, it will give you a very high life, but they are little bit expensive. But maybe the cost, safety, and economics, all these aspects has to be looked into when we select the membranes. So I'm just starting with the basic membrane material, and then we'll go to the novel processing techniques. This is so far whatever I've discussed, I think everybody knows about it, what are the membranes. And if you look at, there are 4 types of different membrane configuration. One is like a plate and frame, another is tubular, spiral wound configuration, and hollow fiber. So plate and frame configuration is just like your filter press. What you have seen a filter press in the laboratory. So it will be just whatever the water or the retentate is passing, it is collected on the other side, and then it either recycled or collected depending upon the use. So we can see that here the flow direction is this, and it is called as a cross flow filtration because the permeate is coming cross here, perpendicular to the flow direction. That is why it is called as a cross flow filtration. Most of the time the people use cross flow filtration. So cross flow filtration, we need to have a lot of material, and it has to be some particular configuration, and then it has to be either recirculated or collected. We need a lot of material in this case. But another configuration is like a dead end filtration. Dead end filtration is we apply a pressure here, and what some retentate can be, permeate can be collected here. Whatever collected will become a retentate here, and then it does not require a very large amount of material. So most of the time, if we want to test the membrane performance, we can use the dead end filtration mode, but we will not have a very high performance in the dead end filtration. We need to have a cross flow filtration because the water flows tangential to the membrane surface. Then only we get a very high flow, very high rate of mass transfer, and then high flux we can get. Here the flux assured is not very high because it is a dead end type of filtration. Just to look at it, how the plate and frame filter looks like it is something like one membrane material, one spacer, one membrane material, one spacer. So whatever feed comes here, the permeate passes through the first layer and collected here, and then whatever retained is, that is retentate, that can be recycled. So this is one typical example of the plate and frame model. Another is like a tubular module. In the tubular modules, the membranes are fitted in the tubes. Okay, membranes are casted in the tubes, or we have a tubular membranes which we can put it here, and then if a feed solution comes here, and then it calculated here, whatever comes out here can be collected as a retentate, permeate here, and then permeate can be collected here. So in case of water, the product, our product is the clean water, whereas the other, the unused water will go here. You have seen lot of water is being wasted even in the domestic RO unit, because that is the water we can collect. Pure water gets collected, impure water which is very high TDS, it will get rejected and goes to the drain. We may use it for the other purpose, garden or other thing. So something in membranes will be here, and then we collect the clean water, and there is a glass, fiber glass tube, and we have several arrangements for the tubular type of membranes. Only concept is here to tell you that membrane is in form of the tube, and it is collected, the permeate is collected, and then retentate is recirculated or goes to the drain. Another configuration is like a spiral wound membrane here, because generally when we make the membranes, we will make in the form of a sheet, and when we make in the form of a sheet, how do we test the membrane? We cannot make the tubes, or we cannot make the flat plate here. So what we can do is we can roll it like a calendar here. The membranes, whatever we have made, we can roll it like a calendar here, and then feed, and we put a spacer in between so that there is a space between the two membrane surfaces, and when it goes here, and then feed water goes here, and then we can collect the retentate, concentrate water comes on the other side, and all tangentially we collect the permeate here. When we collect the permeate, and that is our product sometimes. And if it is a fruit juice concentration, the concentrate is our product, whereas water is very pure water. it can be used for drinking purpose or anything here, which we collect it from the fruit juices. So this is third type of configuration. Another type of configuration is the hollow fiber membranes. Hollow fiber membranes are just like a thickness of the hair, and in that what will happen here, permeate goes inside, and permeate goes in, if you subject it to one just like a hair thickness, and if you look at the hole here, it is 0.1 to 1 micrometer. It's a skin thickness here. If it goes inside, the feed goes inside here, permeate comes out, and then retentate is also rejected here. It gives a very high surface area and a very small volume. So this is also very good configuration here. I think lot of work has already been done on the hollow fiber membrane in the IIT Kharagpur in chemical engineering department by Dr. Day. Professor Day has done a lot of work on hollow fiber membranes, and this is one more configuration and very good. Only thing is that we need to have a cleaning procedure, very rigorous cleaning procedures to be adopted. So basic, again, I'm just coming back to the theory because being a teacher, I want to impress upon more than the configuration, the basic equations which are dealing for the calculation of the flux. If you want to calculate the flux, it is A by N. A by eta, A is the permeability coefficient, eta is the viscosity of the feed or whatever we are using. Delta P is the transmembrane pressure. We just saw that is the average pressure, average feed and retentate pressure. Delta phi is nothing, it is just a difference in the osmotic pressure of the feed and the permeate and the retentate here. And the feed and the permeate here, whatever is coming out. But it is microfiltration, ultrafiltration, it is negligible because we are dealing with the macromolecules. It's not very high, so it can be neglected. And then most of the time we are using J is equal to K delta P. Delta pi we are not using because it is not very significant in other cases. I have just told you about the different mechanisms: solution diffusion, molecular sieve, vapor pressure. Some people have a thought like it is like a solution diffusion. Membrane, whatever the solvent goes and diffuses into the membrane material and then solubilizes and then it diffuses out to the permeate side. So this is one theory, school of thought. And that's it. There are pores in the membranes which block the passage of the solute, not the solvent. It is sometimes difficult to convince and difficult. Sometimes we have to buy some of the logic from the different school of thoughts, because when we do the modelings and like that, we need to have all the things, whether it is a pore flow mechanism, it is a solution diffusion mechanism, or it is a combination of this, or some people have thought it is a vapor pressure, like there are fine capillaries in the membrane which prevent the passage of the solvent, but distillation can take place from low to the high concentration. So people think that these are the membrane has the capillaries which will not allow the passage of the solvent, but it can go when it gets distilled because of the difference in the concentrations. And the preferential sorption, at the membrane surface, the solvent is preferentially absorbed, salt on the surface, and solute is preferentially absorbed. So then this is also one of the school of the thought here. At the membrane surface, solvent or solute is preferentially absorbed. If solvent is absorbed, it will pass through first. If solute is absorbed, that will also pass through first. But there should be a differential. Differential of sorption should be there. And there is like a hydrogen bonding. It is like a hand holding. Like it will bind with the hydrogen present in the feed, and it will allow it to pass through the membrane material and then collected at the permeate site. All the mechanisms, all the 5 mechanisms play an important role in the different scenarios, but generally first 2, like pore flow and the solution diffusion, they have a lot of significance, and most of the modeling in the membrane have been done based on these phenomena. So what are the different characteristics of the membrane? We look at this now. If you go and buy the water purification system, there are I'm not advertising for anything. This There are so many 0B, Kent and like that coming. What should be our criteria? What should we ask? It should be have a very high water permeability and high solute rejection. So 95% of the solute should be rejected. Minerals should be rejected, because suppose we are getting a very high TDS water, a very high hard water, it should reject around 90 to 95% of the solutes. Then only it is fit for the consumption. Another thing is that we look for that how long is what is the shelf life of the membrane. Like if suppose we buy now, can we can we use it uninterruptedly for at least for 3 years? And then after 3 years, the cost of the changing membranes and filters, it is around 50% of the cost of the equipment. So those are the parameters we generally think before we buy any membrane unit, even for the house or our pilot plant or anywhere in the industry. And ultra thin RO membranes, what are the membranes they are giving to us? Because Ion Exchange has opened up their unit probably in India. I came to know that's why membrane processing RO has become cheaper in India. Otherwise, when we are importing this, it used to be very high. And now these membranes are only cellulose acetate, mixed cellulose, esters, polyamide, polyurethanes. These are just the polymers. And whereas if you look at the ultrafiltration membranes, ultrafiltration is generally used for the fractionation or the maybe we can remove the separate the different kind of enzymes of having the two different molecular weights, or maybe for the pectin removal from the juices we can use ultrafiltration. It should be very mechanically very strong, because we need to apply a pressure. It should have a high mechanical strength, durability, and even if it cakes the deposited on the ultrafiltration membrane, we need to apply a still higher pressure. And it should be resistant to abrasion, heat, hydrolysis, oxidation. Well, these are generally things come with when you buy the membrane, and it should not creep, soften, collapse under pressure. It should be stable. What are the different applications in the food processing? Like if you look at this, these are not the exhaustive list. Any of you can think of number of applications. And it is like, I'm just giving you the example. We can concentrate and purify fruit juices prior to evaporation. Generally, fruit juice, if you evaporate the single strength juice, it's not economical, because when we extract it is 10 degree Brix. It has lot of water, and if we send it for the evaporation, it requires lot of energy. So what we can do is we can evaporate and concentrate the juices, and then only we take it to the further processing. Concentration, we can use it for the concentration of the starch, citric acid, egg white, milk, coffee, syrups, natural extracts, flavors. You name any process, we will be able to use the membranes. And it is for the best example for this, that it can clarify unwanted suspended particles. It can clear from the wine and the beer, and it gives you crystal clear beverages. And the fractionation of the fermented liquor, suppose we are producing some fermented liquor like wine or something, so we can fractionate it, maybe whatever required we can keep, other things can pass it through. And another thing, we are emphasizing on the demineralizing and purifying water. So demineralized means very high quantity of minerals are there that can be demineralized, and then we can purify the water using the membranes. It is already come in place, and even the government has put up a unit, maybe I don't know the other states, Karnataka, the Tata and so many private companies have put, we can take our box and get the 25 liters of water can be collected only for 5 rupees for drinking purpose. And it can be used for the removal of the monovalent, polyvalent particles, bacteria, organic material with molecular weight greater than 300. Maybe, I don't know whether this is the first ever patent taken by FAO. What they have done is, they have passed the tender coconut water through the membranes, and then they have shown that there is no microorganisms present in here. Membranes can remove all the microorganisms. and then the product remained the self-stable. This is the first ever patent taken by FAO. FAO generally funds the researchers. They don't take any patents. But when they found it very interesting, membranes can even pasteurize a sterilized type of the product, and the product can be preserved for a longer time. So it can be used for the concentration of the milk and whey prior to the processing. Maybe I heard a story like that. This our laboratory NCL Pune works on the membrane processing. When they started working on the concentration of the milk, and from where they'll get the milk, because milk is an expensive material. So they have sounded to many of the dairy industries, and they said, we are going to concentrate the milk. We will concentrate the milk and give it to you. It is up to you. You do whatever you want to do it. But otherwise, they have to use lot of time and energy for concentration. And many people offered, and they came and concentrated the milk using the membrane processing for free. And they concentrated, and the scientists collected their data, and they showed that it is feasible to concentrate the milk. Maybe you can produce the condensed milk, spray-dried milk, because it has to be concentrated. And whey also can be concentrated, like whey protein isolate nowadays. It's a very popular ingredient. So that also can be concentrated. Other applications, if you look, we can concentrate the protein solution, and we can make in a protein flakes. And fruit juices can be concentrated. Enzyme extracts can be concentrated, and cold sterilization, whatever I just told about the tender coconut water, same thing is true for the mango pulp. If we pass the mango pulp, sometimes the microorganisms will get filtered. It will not go through the permeate side, and it will go to the and then we get a pasteurized sterilized pulp. It has a lot of application. The oil processing. This is our current area of the research here. We are using the membranes for the oil processing. Oil processing is the non-aqueous processing of the oil, edible oil. When we solvent extract the oil micella comes with like 25 to 35% micella comes with a lot of hexane, and hexane has to be removed by the application of the heat. And whereas in case of solvent resistance membranes can remove the hexane just by membrane processing without heating, and then we can at least 60 to 70% of the energy can be saved, maybe carbon footprint and all those things we can save here. And this is a project running with the help of the support from the Ministry of Food Processing, and we are almost going to conclude it by putting a small plant in a local oil processing unit, and we will demonstrate that it is possible to remove the most of the hexane in the oil processing just by the membranes without heating. And it has other processing steps like coconut processing. We can concentrate coconut milk. Honey processing we can use. Like most of us travel in the aeroplane, and you see that sometimes if we don't want sugar, we ask for the honey to put in the coffee. So this honey is not that a natural honey. This is natural honey, but what they do is they add water, and then they filter it using a membranes, and they concentrate it again using the membranes, and then pack it in the sachets and give us. So in the process of diluting honey, they remove the lot of whatever the yeast present in the membrane, it is removed, and then they concentrate it again to the same consistency to 18% of the moisture content, so that no yeast, even if it is present, should not grow. So that it has a lot of clear honey is made using membranes. An application of the dairy processing, you have already heard about that. We can concentrate the milk for the condensed milk, or this spray-dried milk we can use. And membranes has several other advantages, like we can immobilize the enzymes on the membrane surface, and it can act as a continuous bioreactor. Suppose we can immobilize some enzymes like invertase or something like that here, and we can pass through the sucrose solution we can use. Invertase is already immobilized on the membranes, and when it passes through, it will change into the glucose and fructose. And generally we set in such a way that we produce a high fructose syrup. That is very much demand in the sweet makers actually. The people want to use a high fructose syrup than the sucrose, because high fructose syrup gives us a very shiny appearance in the sweets, maybe the cashews, burfis and all you are seeing. It is people are using, the local people may be using sucrose, but the popular sweet makers are not using sucrose. They use the high fructose syrup, which gives us a shiny appearance and the better quality of the product. And there are companies making high fructose syrup. There's anywhere in the, like, it can be used, it has many applications. So it is all possible because of the membranes. So effect on the food, if you look at this, it has, see, we are not going to heat the food product because whenever you are using the membrane, so it has a good retention of sensory and nutrition quality. So all the nutrition sensory qualities are retained. And even the functional properties like protein, if you see, like
Sir, I think you get muted. Sorry for that.
Please unmute, Rastogi ji, unmute yourself. You are muted. There is some problem. आपका माइक म्यूट है प्रोफेसर रस्तोगी, अनम्यूट करो आप. हाँ, yes.
is that okay?
Yes, sir, it's fine now.
Now it's fine.
Okay, now I'll attempt sharing the slides. Can you see the slides? Hello?
Yes, sir. Yes, we can see the slides. But if you can make it in presentation mode.
Is that comes to presentation?
Sir, not yet. I think that sharing the entire screen would solve the problem.
Slides are visible?
Yes, sir. The slides are visible.
Okay. So till now we talked about the existing membrane processing. We will talk about the novel membrane processes. In that, earlier what we have seen, the concentration we can do up to only 25 degree Brix. We cannot go at a very higher degree bricks because it still has a lot of water content, but even then lot of water is removed, but we can use these membranes, some other membranes, for the concentration up to 60 to 70 degree bricks. Okay, so there are several two processes. What we have worked is osmotic membrane distillation, and this is like a forward or direct osmosis. We can refer it as FO or DO. And osmotic membrane distillation is a OMD process. Here the difference between these two processes is not very high. Here we use only hydrophobic membranes, where in case of FO we use hydrophilic membranes. The type of the membranes which are used here are only different here, and when it is hydrophobic membrane, it will not allow water to pass through as such. So how the water will pass through? It will go in the vapor pressure difference is the driving force. Water will get converted into the vapors, and then it passes because of the vapor pressure difference. Whereas in case of forward osmosis, it goes as a difference in the osmotic pressure. You remember we had a delta pi was the term there. So we encounter with the delta pi here, whereas here it is a vapor pressure difference is the driving force. And we can concentrate up to 60 to 70 degree bricks, any product, just by using the membrane technology. And then because we are not using any heat here, so all the organoleptic properties, functional properties, and the characteristics, everything remain the same. Maybe we have some samples. Please be patient. We'll show some samples as well as the chemical characteristics of the concentrates as well as the reconstituted products. If you look at what is that osmotic membrane distillation, if you have the liquid, what we have to do is we have a liquid phase on this side, and this is the membrane, and we have a liquid permeate on the green side is the permeate here. So what we have to do is,
are you moving the slide? Slide is not moving.
Like?
We are in slide number 26, that is novel membrane process.
This one? Can you see this one?
No, only 26 slide is there. 26 slide we are seeing, but it is not moving. And now it has come 28. So earlier we did not. You can go presentation mode में थोड़ा सा चले जाइए F5. You can press F5. कुछ प्रॉब्लम है नेटवर्क में लग रहा है. Yes. Now it is moving at least. Osmotic membrane distillation. We are seeing.
Sir, I think you are
not audible.
You are muted again.
अनम्यूट करो आप. अनम्यूट करो अपने.
Sir, I think there is some bandwidth problem. If you close your video.
हाँ, थोड़ा वीडियो ऑफ करके तब करो. देखो
Yes, sir, आप अपना वीडियो ऑफ कर दीजिए तो थोड़ा नेटवर्क स्ट्रॉन्ग हो जाएगा, बैंडविड्थ स्ट्रॉन्ग.
देखिए अभी कैन यू हियर सर?
नहीं, हाँ सुन तो सकते हैं. प्रेजेंटेशन में जाओ आप.
एक्चुअली यही ज्यादा.
आप जरा अपना वीडियो ऑफ करके एक बार ट्राई करो.
ओके.
क्योंकि बैंडविड्थ का कुछ प्रॉब्लम हो रहा है. सो इट मे इम्प्रूव इफ यू स्टॉप योर वीडियो.
Is that slides clear? Can you hear?
Yes, it is clear, but not in the presentation mode.
Now? Yeah, only, but I am not. Okay, I'll do that again. If I do this, I see only the presenters here. I don't get my slide here.
नहीं आप देखो नीचे एक एरो है ना, एरो प्रेजेंट नाउ.
Yeah, I've seen. Share your entire screen.
You click entire screen. You are click on entire screen. Then share button will activate नीचे.
Yes, sir.
तो उसको आप क्लिक करो.
You are presenting your screen.
हाँ.
And now you can see.
Yes. Yes.
Yes. Now it's.
Now it has come full screen and excellent.
Okay, so there is a little animation just to show that whatever blue color is there, this is the water. When it crosses the membrane, it changes to vapor, and then being in the vapor phase is transferred. Again, it gets converted to the liquid state and comes here. That is called as a osmotic membrane distillation, because distillation is taking place across the membrane and it changes the form here and then comes in the form of a vapor and comes. And requires a hydrophobic membrane, and only water can pass through here, because water only can vaporize, or the other solutes and nothing can vaporize, so only water. But the problem is here, the flux is not very high. So there is another method like called as a direct osmosis, or it is forward osmosis. In this case, there is no phase change, water passes as such, but there is a bit of problem. Some of the salt, whatever we are using circulation here, that will also pass through the feed side. Feed gets concentrated, but some of the salt will also come to the liquid phase. Then there should be a strategy to reduce the salt transfer, reverse salt transfer to the feed size. And in this case, we are using hydrophilic membranes. Hydrophilic membranes is there is no feed phase change, only water transfer as such. But whereas earlier case, osmotic membrane distillation, both are almost same, but only thing is mechanism is different. There the water changes its form from the liquid phase to the vapor phase, and then transfer and then condenses again in the liquid phase. So if you look at this, how it works here, this side is there is a feed here, and the feed goes here. This is a membrane. This feed goes here. It works transiently, comes here, gets concentrated. Whereas this is a draw solution, which goes here like a salt solution, goes here and then comes here and then returns back. The mass transfer takes place across the membrane. Water flux is maintained here. Water gets transferred. This draw solution or osmotic solution will get diluted, whereas our product of interest will get concentrated. So in this way, we can circulate the product and get the around 60 to 70% concentration we can achieve. We can do it as long as we can circulate the liquid, because at a higher concentration viscosity increases, then we cannot do it higher concentration, and when we stop. We have done it for the several liquid foods like pineapple juice, sugarcane juice, coconut water, tender coconut water. We have several patents on that, concentrating tender coconut water by this method, and then it can be redissolved, like 1 teaspoon of tender coconut water can be dissolved back into 1 glass of water, using 1 glass of water, and it still gives a taste of the fresh tender coconut water. So this technique is known as a forward osmosis, because lot of, otherwise if you are not concentrating, we need to transport lot of water, and unnecessarily it costs money to us. So it is better we can remove the water, and at the point of the consumption we can reconstitute and then bring it to the same concentration, and some reverse salt transfer will be there. That can be avoided by having a different strategies. We can have a mixture of the salt and the sugars, or we can have a different draw solutions The people have worked on the different draw solutions where we can restrict the reverse salt concentration, but product can be concentrated up to 60° Brix, and if you concentrate anything above 60° Brix, it does not require any preservation methods, and maybe we can store at a chill temperature with a little addition of the sugar, but it is also not required once we achieve more than 60° Brix. So how the forward osmosis works, this is, we have seen the concept here. Just look at here, this is a simple process of osmosis. If we have a feed, concentrated feed, if we contact it with the water here, water will slowly start moving to the concentrate solution. And second thing is that here this is called as a reverse osmosis. If you apply a pressure, the water will start moving to the water side here. The feed, water from the feed will start moving to the water side here, and this product will get concentrated. This is known as a reverse osmosis. What we are doing is here, this is called as a forward osmosis. We have a feed here, and we have a very concentrated solution like 6 molar NaCl solution. So what will happen? Water will start moving under influence of osmotic pressure. No pressure or temperature is needed. Only osmotic pressure can transport the water from the feed side to the draw solution, and then it gets concentrated, and it can be concentrated up even up to 60° Brix or more than that. And only thing is a matter of circulating in the tube, and how can we circulate this. And then one more concept is here. If we are circulating and we restrict it here, if we restrict here, we do not allow the draw solution to come here, it will create some kind of a pressure. This phenomena is known as, this is known as a pressure retarded osmosis. It can even be used for the generation of the electricity. So we are restricting our discussion only till the forward osmosis, and this is another phenomena which can be used. So what kind of the membranes are this? If you look at the membranes used for the forward osmosis, generally they are not available in our country, but people can make, and these procedures are available. We can make. Only thing, it may give us a little lower flow rate, but these are the flow membranes. I can give you the specification. You can think of how to make it. It is generally less than 50 microns. It is something like embedded. These are the membranes embedded in the polymers, but total thickness will be less than 50 microns. So some people are making, even in India, some research institutes are making, and even the publishing the results. But some of the membranes are available outside. Even people use available. The forward osmosis membranes are available. People are buying, using, and can do the experiments and concentrate the liquid. Only thing, we still have to bring it up a commercial scale operation. If you look at how this is happening here, this is the mechanism, because we don't leave anything without the mechanism how it is happening. So if this is the forward osmosis membrane, there is no, because I was just discussing, membranes has to be supported with a support layer like this, either on this side or on this side. If we do not, if I have only membrane here, then it is membrane, it is something like this here. And if we see here, what is the driving force is pi d minus pi f. Pi d is draw solution side, osmotic pressure on this side, and pi f is the feed side. But only thing, it is difficult to withstand that this membrane here, because there is no support here. If we provide a support here, membrane become very thick, and then if it becomes thick here, what is happening here? This is a feed is here. If feed goes here, it goes inside, and it becomes concentrated till here. Actual membrane starts from here. Otherwise, this is only a support layer. Actual membrane processing starts here, and this type of polarization is called as a concentrative internal polarization, because the feed gets concentrated from here to here. After that, the migration of the water takes place. So in this case, what happens here, we can have, if the feed is, if the support layer is on the other side, what is happening here is that this is the actual membrane processing ends here, but after that, there is some kind of a, whatever the salt present here, NaCl, it will come inside, and then it will further dilute the here. So that's why it is called as a dilutive internal concentration polarization. So there are two kinds of internal polarizations, and we can put the membranes in the two settings. See, the literature of the membrane processing was it's very confusing, because nobody tells what is the mode they are using, how they are using, what is internal concentration, what is dilutive concentration. So that's why we have for the first time we have published in the journal Separation Purification Technology about the mechanism of the forward osmosis, how it takes place, and made it very clear that the way you keep the membrane has an impact. And sometimes people buy the membrane and they say it's not working because the orientation where they orient it was not correct, and then we changed the orientation, it started working. So please look at this. These are the concentration polarizations which were not at all discussed in the literature, and for the first time it was made available by our work here, and then now everybody is almost using. And if you look at this, another thing here, when the feed will not have only single molecular weight compound. If it may have a low molecular weight compound plus high molecular weight compound. If it is a low molecular weight compound, this can cross through the boundary, the support layer, and the actual membrane processing will start from this point onwards. And if it is a high molecular weight compound cannot go inside. It will be retained on the surface. Only the low molecular weight compounds can go inside, and then only the migration of the water will start. So these are the things which has been clarified and published widely in international journals, and means our group took a lead in explaining the concentration polarization and as well as the processing the whatever the mechanism involved in the high and low molecular weight. And then we have shown that if you have a mixture of this, the mode 2 whatever we are using, the feed is towards the active layer. This is active layer, and this is the osmotic agent is toward the support layer. This was found to be the best combination, giving the highest flow rate. How much time I have? Can I continue for some more time?
Yes, please continue. Please continue.
Okay. So again, this is the same equation. Membrane processing applies here. Only thing what we are talking earlier is about A into delta pi, and now this delta P may not be significant so much, but delta pi is very significant. Delta pi is the difference in the osmotic pressure of the draw solution as well as the feed. Draw solution we select in such a way that it's having a very high osmotic pressure, and the feed as compared to the feed solution. And then we have this equation, same equation we are using to calculate the flux here, and A is the permeability. So same thing again, we just wanted to show you how it is happening, just a revision here, how it is going here. This is the feed is going here, concentrating here, feed is coming back, leaving the water on the other side, and this side draw solution could be NaCl solution, calcium chloride solution, any solution having high osmotic pressure. It could be newer solutions, inorganic solutions, and then it can be concentrated. Our liquid feed can be concentrated. And this is the experimental setup. If you look at this, whatever we have shown, this is the membrane setup we have, and both the sides. We are concentrating the anthocyanin from the kokum fruit, and you look at it here. We have a NaCl solution. It is being concentration. There's no transfer of the color. This is absolutely transparent, whereas this is very red here. So there is no transfer of the anthocyanin taking place here, and then we can monitor the flux, concentration, bricks, everything we can monitor, and how much we can concentrate. And this is made by us only. We have made it. We have got the we have done in our laboratory. We have done with the different materials. Like our main focus was on the concentration of the natural colorants. Another was the fruit juices, because both will when we extract, it will have a very low concentration, and exporting there is no technique which can concentrate the natural colorant, because moment you heat the anthocyanin, there will be change in the anthocyanin composition, and then it will become like a brown, and then we cannot have this, but we'll show you some of the pictures. So we have done, like, if we can change the osmotic agent concentration, like 1 molar to 6 molar we can change. If we increase the osmotic agent concentration like NaCl, then it will increase the water flux. Like, why it is? Because if we increase the concentration, water flux will increase, as well as it will increase the anthocyanin concentration. So water flux is also increasing, anthocyanin concentration is also increasing. And if we change the temperature, we just discussed, if we change the temperature, osmotic pressure will be higher at higher temperature. We wish to operate the forward osmosis unit at higher temperature. We could not do it because anthocyanin cannot be heated more than 40 degrees centigrade. And what we have shown here, if you can heat the anthocyanin up to 40 degrees centigrade, flux increases, exorbitant increase in the flux. Anthocyanin content is also increased. But only thing, we cannot heat more than 40, and there is a and we have selected mode 2 was found to be the best one. Earlier also we have shown mode 2 is like feed is towards the active layer. That was found to be the best one. And this is like osmotic agent flow rate and feed flow rate also we can change. So this we did not find a much significant increase that. In the flow rate does not change much the flux as well as the anthocyanin concentration. If you look at this concentration, overall concentration, we have just put this. Kokum is the fruit. Actually, it is very much used in some of the part of the countries, and maybe in the Western Ghats for the using as the acidulant in the many of the food preparation, and it is a good colorant and with a cooling effect, and lot of it is used in cosmetics as well. So when we extracted, it was only 2 degree Brix, and we could increase up to 52 degree Brix in only 15 to 16 hours, and we concentrated up to 52 degree Brix. And there is, of course, when we increase the concentration, flux is going to be decreased, and when the flux decreases, maybe we can have a strategy to clean the membrane, put it back again, and then again get the same concentration. So it is concentrated so much, 70, anthocyanin was concentrated to 71-fold enhancement was found. And without, there was no change. When we diluted it back, we have got the same anthocyanin, which is not possible by any other way. Thermal treatment will spoil the anthocyanin content here because it leads to the production of the brown pigment. We have just compared the fresh, this was the fresh extract of kokum. This is the forward osmosis concentrated one. And when we thought, let us dilute and see whether there is any change in the, after we dilute it, is there any change? It was found that almost absolutely there was no change. Like fresh extract and the reconstituted extract has the almost like 2 degree Brix we did, and then titratable acidity was little bit reduced, but it was okay. And then color parameters we estimated, density we estimated, viscosity, it was almost same. So there was no change because of the forward osmosis what was happening here. So we excited with the work what we did. We wanted to take the our work further, and then we thought, let us try with there is a problem with the concentration of the betalins, like from the beetroot. So then we concentrated betalins. We stopped the betalins after 6 hours and then reconcentrated again. So if you see here, 57-fold concentration in the betalins was obtained. Otherwise, if you use any thermal processing, it will degrade. It is not possible to concentrate up to that concentration, and it will produce a brown pigment. Same way, we excite again with that result here. We concentrated the pineapple juice because we have seen after second cycle also it is reducing the flux. Then we have gone up to 3 cycles, and then we can concentrate up to 12-fold. We can concentrate the pineapple juice, and when we concentrate it juice, and whenever we want our juice, we can dilute it and consume it here. And again, anthocyanin in a different experiment like that here, it was concentrated, we concentrated 6.8 folds in our and the bricks was soluble solids were around 12 folds we can concentrate. Means it shows that it is possible to concentrate. Only thing, we need to stop the operation, clean it back again, assemble the system again, and then concentrate again, because there could be some kind of a polarization, concentration, polarization, plugging, and like this, that we need to restore the membrane, and then we can do it, and then we can see that we can increase the 4 cycles anthocyanin 6.8 fold, 104 to 71 we could concentrate. So again, beetroot juice was concentrated. Just to give you a overall view of this, we have concentrated using the forward osmosis and compared with the thermal processing as well. What are the changes take place in thermal processing and what are the changes takes place in the forward osmosis. Just to give you a gist of it, like it here, we could concentrate forward osmosis up to around in 12 times we could concentrate, and there was a flux decrease because as the concentration increases, flux will decrease, and then there will be a reverse salt migration also was taking place. So that we could do it by having a combined reverse draw solution. Like we can have a combination of the draw solutions like sugar and salt mixed together, and different number of the combinations we can think of. We can have a magnetic nanoparticles as a draw solution, or carbon fibers, or there are different things are available just to avoid that. And FO concentrated, we have extracted the color from the rose petals, and rose has also anthocyanin, and it is very difficult. Like moment you heat the rose, the color of the rose will go and it will not be useful. And we have shown that the rose colorant will have a application in the food processing, because it can give a very good red color, and whatever the red color it gives, it is very stable. So like how do we extract the rose? Control was giving us like this 100%. We dipped the rose in the liquid nitrogen, extracted sonication, 30% alcohol, freeze and thyme. We almost left, we did not leave anything. All the methods we have tried, we thought without using the alcohol, freeze and thaw was giving the best, and we extracted it and then concentrated using forward osmosis. The flux decreased, but the concentration of the anthocyanin increased many folds. So this is the crude rose extract. Maybe I don't know whether anybody of you have seen what is the color when you extract the rose. It gives this kind of color. This is anthocyanin. When we concentrated by using forward osmosis, it was like this, and when we reconstitute it, become like this. So there is no difference between crude and the reconstituted one here. Almost it is same. And when we wanted to use in some of the foods where it can be used, we have chosen that we can use the fresh yogurt, and then we thought rose gives a very good essence and then color also. So we thought to use it with the yogurt, and when we add it here, if you compare this, rose forward osmosis concentrated yogurt, forward osmosis concentrated rose color, when we added it has a highest shelf life as compared to the thermally processed rose color. So we try to just compare. So because there were a lot of changes take place during the thermal processing, so we avoided the thermal processing, and then we concentrated by the forward osmosis, which gave a highest shelf life. And this is the K values and all those things we have calculated, and it showed that product storage at 4 degrees centigrade had a very high shelf life. So sometimes we see that the forward osmosis has a low flow rate. So what we thought, we can use the ultrasound to increase the flux on the flux during the forward osmosis. So we applied the ultrasound on both the sides of the forward osmosis. The idea was to dislodge the concentration polarization, because both the side liquid is flowing, and both the sides the concentration polarization may not be very high, but there could be some kind of some layer formation or something will be there. So we put it to the ultrasound here, and then whatever like we applied the ultrasound, it did, whatever that came near the membrane surface, ultrasound almost dislodged everything by the its power here. And then ultrasound, we have made new process like that, ultrasound assisted forward osmosis concentration process, because otherwise you have to clean it very often. Here you don't have to clean very often, so you can dislodge the cake or whatever the cake or the concentrated things are deposited here, which can be dislodged by the application of the ultrasounds. So what we found in the during the ultrasound and forward osmosis, so without ultrasound, this was the without ultrasound first one, and when we did with ultrasound, we found that feed volume reduced, means there was a good reduction in the feed volume. And when pectin was not present, only sugar was present here. When the pectin was present here, like higher concentration, 0.5% or minimum percent or these things, there was an effect, but not very prominent effect. So we are still looking for a method whether to degrade the pectin, recover the pectin, and then subject to ultrafiltration, because it may not be very feasible to work with the forward osmosis when high content of the pectin are present. So maybe we need to degrade the pectin and then go for the forward osmosis. So this figure clearly indicates that ultrasound is very effective in reducing the volume, and we have put in how much is the reduction in the feed volume we could observe. So it was very effective. Without ultrasound it was reducing this much, but with ultrasound it reduced a very significant amount was reduced. And probably these findings were published in the ultrasound sonochemistry. And this was the first approach that ultrasound can influence the flux in the membrane processing. After that, lot of papers have come, even in the ultrafiltration, reverse osmosis, people have started using, and most of the genesis of this is the paper which we have published in that, because ultrasound influences the flux. And then based on that hypothesis, lot of papers are coming up in the literature these days. And only thing, we are still finding a solution, like how to avoid the increase the flux if the fruit is having a higher pectin content. And we have done with the sweet lime juice, like that it was shown. See the other this is for the sweet lime juice we have shown, where pectin was not very high. And first two are the model systems. And here I was just telling, there was a reverse salt transfer also takes place. This is the salt transfer. If you look at on this axis, so salt transfer increases with the concentration here, and that is sometimes it is not very acceptable. Like fruit juice having a salt taste, people may not like it. But only thing is here, we are not going to consume the concentrated fruit juice as such. So we are diluting it and consuming. So once we dilute it, this is a very minor amount. Once we dilute, it does not require, you cannot get the taste of the salt. If you get the taste of the salt, we have two strategies. Like we can have a sodium chloride as a draw solution, or we can have a sucrose as a draw solution. So we can combine these two solutions, mix these two solutions, and can get that, so that we can minimize the salt transfer while maintaining the same flux. And this maybe you can find this paper published in the Journal of Membrane Science. For the first time, it was shown that we can have the two mixture of the osmotic solutes, and while reducing the salt, uptake, or reverse salt transfer. Look at this. This is the thing here. What we obtained. This is a fresh pineapple juice. This we have clarified, because this pineapple juice cannot be subjected to forward osmosis. We have clarified it, and then it becomes like this. Then it is concentrated by the forward osmosis, and then again when we diluted away, it came to the clarified one. And then it can be either the osmotic membrane distillation or forward osmosis. It can be used in any way. And if more than that, we have done in our sugarcane juice also can be concentrated by this technique. And we started working with the different colorant from the obtaining from the different flowers. And there is a big mission project going on at CSIR, and we are a part of it. We are recovering the different bioactive compounds from the different colored flowers, and then could be we are extracting blue, red, different colors, which will have applications in the food processing. Another very interesting application, probably this is the last one. Okay, so thanks for your patience. And here, this is a very important application. We can make a bag out of the forward osmosis membranes. And we have put some kind of a sugars and some other thing inside. And what will happen here, see, when the people working, like army, the defense forces working in the terrain area, difficult region here, they do not have a drinking water. So suppose if we have this kind of bag, and the drinking, if they have a dirty water or not a potable water, we can hang this bag in the potable water, maybe not a potable water. So what will happen? This bag is made of forward osmosis membrane. It will suck the water inside. When it sucks the water, this bag will be filled of the water, and we have already added some nutrients inside, like vitamin C, some sucrose, some glucose, like that, and it makes a very tasty drink inside. And even the soldiers at the different locations can have this kind of water, and it will be like a fruit juice for them. And we can add some dried fruit juices, and when there is no water, we can generate water. So this is the last slide. We all wait for this slide, actually conclusion of the things here. I will say that it is a very exciting and emerging technology which has not been explored much here at the moment. And another thing is that in India it is flourishing very well. Most of the work on the food processing are reported from the Indian laboratories. And only thing is that we need to work more on the generation of these kind of membranes. Where do we get these kind of membranes? Formation of the membranes. The membrane institutes, people working with the formation of the membranes, like casting of the membranes, comes into the picture. And when this is solved, I think the sky is the limit for India to catch up in this area, because we have cleared almost all the mechanisms. Everything is done in our country. And another thing is that we need to have a draw solutions. Suppose we have a magnetic draw solution, which suppose magnetic draw solutions containing iron particles. So we can have the iron magnetic particles in the draw solution, and just add that magnet, all the draw solution will get cleared, because magnet will attract iron particles. So this requires a research in the 3-4 areas, like membrane making, draw solutions, different applications. And I think while attending this talk, you must be thinking, I also can use it for my application. Most of you are the students or the researcher or the faculty. You can think about, I think we can also use this technique probably, and maybe when the synergy happens, then only we can attain the full scale potential of this technology in the food industry. And I'm proud to say that India is in the forefront in developing this. And I would like to thank Professor Mishra. He gave me this opportunity for publicizing this event worldwide, giving this opportunity to present my work. I had got many calls from US, UK and different countries. Okay, I also like to join. I said its link is available at IIT Kharagpur. You can also join. And my thanks to my director, Dr. Sridevi and Purna Singh, and for giving me permission to present the talk, which might lead to the future collaborative works, which will always be looking to new areas. Maybe you people, the different people, those who are listening, new brains, you may have a different, more innovative ideas. We would like to encash upon that. And I would like to express my gratitude to the faculties, students, mentors worldwide for joining this event for different institutions from India and abroad. I think There are many people joining from the US, UK, and the other different part of the world. Thank you very much for this for your attention, and I once again I thank the organizer for giving me this opportunity, and it's a very interactive platform, making it in the form of the webinar. Thank you very much, sir.
Thank you very much, Dr. Rastogi. It was a very elaborate and excellent presentation, very nice information. I'm sure there must be a lot of questions, enthusiasm. So
Yes.
there are already a few questions on the chat box. So Manas,
Yes, sir.
you'll be reading, you can read those which is already on the chat box.
Sure.
Even we can invite the people, they can themselves ask, they can open their video, so the session become more lively and interactive. Okay, please continue.
Indeed. There's one question by Dr. S.K. Pandey, who is asking about the cost of operations. A discussion on the cost of operation.
Yeah, cost of operation. See, in the membrane processing, the most notable cost goes to the membrane. Like earlier, why we were not able to use membranes in India, it was because the membranes were very expensive. So now also for novel processing operations, it has become very cheaper because some of the companies have opened the companies like Permianics, Ion Exchange and Kent and so many things. Anywhere you buy the RO unit, you will find that membrane is manufactured in India. So that's why it has become cheaper. So for the novel operations, we still need to work on the making.
I lost the connection.
Yes, sir. Yes, sir. It appears. So, some network connection there, problem is there. Professor Rastogi, you are muted. You have gone muted. आपको बीच-बीच में नेटवर्क जो है म्यूट कर देता है ऑटोमेटिकली.
Mishra ji, I have a very simple question. Maybe anybody can answer.
Sir.
In big societies where you have hundreds of apartments, the RO water is really a big issue. People like to have a big unit,
Yes,
supply this good quality water to every apartment.
Yes, sir.
But water quality varies from the one complex to another.
Yes.
And so are there systems where we can decide not the TDS only, but which minerals in what quantity we should allow? Upper limit on different minerals. Is there a system? Do we have membranes and systems so that we say we don't exceed this on that? Total TDS is that is there.
Yes, sir.
But then it's a combination of so many minerals.
Yes, exactly.
But can individual minerals be controlled?
I don't think the membranes can control the individual minerals, but what I heard, like suppose we have water which is coming from we have a Kaveri river water. Kaveri river water TDS is around maybe 60 to 70. So we don't need a membrane processing system. We require membrane processing to clear the microorganisms, not to clear the TDS. But in the same state, if you go for the borewell, here the borewell will have a 500 TDS. I am not really not aware the combination of the minerals. Maybe somebody else can enlighten this. Maybe the calcium has to be reduced probably, because what I have seen, when we are using borewell water, even if you wash your car, you will find the white spots deposited on the car. So you are not washing your car, you are dirtying it. So maybe that kind of concept of the mineral water, somebody maybe can clear it. I am not sure about it, sir.
Well, Navin, you understood the question, but I think this is a big issue.
Yes, sir.
That people and calcium is definitely a major issue.
Yes,
so
sir.
I think
I really need to learn some more about it, sir.
Okay, thank you.
Thank you, sir.
Yes, there are a few other questions, I think.
Yes, sir. There's one more question. Meera ma'am is asking, does this method affect the stability of natural enzymes found in foods like juices?
No, because this is at the ambient pressure and the ambient temperature. It will not affect the enzyme, any functional properties of the enzymes. The only thing is that there could be possibility that when you are circulating it for a continuous, maybe for 5 hours, 6 hours, the shearing of the pump may produce a bit of heating. I'm not sure that, because the people have started working in India, even in maybe the whey proteins and all other things here, but we are not sure that. But what literature reports, there is no change in the functional properties of the protein. And I'm thinking same thing can be extended to the enzymes.
Thank you, sir, for the answer. And there's one more question from Shaba Noore. She's asking, greetings from Ireland. Sir, could you please enlighten us if it is possible to remove chlorophyll from vegetable oils using RO, FO, etc.? And if yes, then could you please let us know which type of membranes shall we use?
See, actually, it is not really possible just to give a ready answer for this, because it is a matter of R&D. Like the chlorophyll itself is a water-soluble compound, and we need to really work on it and see that it is not. There is no ready answer for this, because if it is water's concentration is possible, fractionation, what are the things has to be separated. Like we need to study it's a combination of chlorophyll A and chlorophyll B, and which kind of chlorophyll we need to differentiate between the properties of the chlorophyll. Then only it will be possible. I don't think I have a ready answer for this.
Maybe some functional membranes can be tried.
Yes, sir. That could be possible.
Functional membrane, not by the normal membranes. Yes.
Thank you, sir, for the answer. And we also have one question from Ashish Sharma. He says, excellent presentation, sir. What is the normal life of Indian-made and imported membranes used for fruit juices?
Yeah, thank you for the appreciation. And see, membranes are membranes, whether you take it from India or abroad. So, what I have seen is that whatever made in India has a very high stability. Whatever comes from other country, even the diseases do not have stability. So, as long as suppose it is a polysulfone or any other material, it will be as good as the imported. We are working with there is an institute, CSR institute, that is called as CFTRI in Bhavnagar, and we are working on the non-aqueous application of the oil for removing the hexane, as well as for the removal of the other impurities from the oil just before the pre-treatment, because we do not want Misila to go for the removal of the hexane by thermal processing. And in that case, we have taken some of the membranes from the German membranes and some of the Denmark, and many membranes we have taken, and we have made our membranes in the CSIR membranes. We have found our membranes are much better than any other membranes. And please don't quote anywhere, I'm just giving you that the cost of the membrane, if you compare, 1 square meter will cost you more than ₹1 lakh if you import. But if we make it here, it may be 1/10 times of this, and we can make as many as sheets want. Research is not successful in a single attempt. We have used so many modules, like we have in collaboration with the Permionics, we have in collaboration with CMCRI. They have all, from past 3 years, we are working on the membranes for the edible oil processing, and now only we are successful in developing an Indian membrane which gives almost same performance as the other country membrane. And if you compare this, our membranes are much
Again muted. Please unmute.
Sir, could you please repeat? Actually, we're not. I think the connection was lost.
His connection is lost.
Yeah, please repeat.
Yeah.
Sir, could you please repeat from like where you stopped? I mean, you were talking that the Indian membranes have certain advantages. I think there's where you lost your connection.
Yes, because we have a institute, CSR institute, working only on the membranes. So they are working on the we are working on the non-aqueous membranes for removal of the hexane from the miscela. And there are one or two companies in the world they are making. We have got brought their membranes. We compared with the Indian membranes. Our membranes were much better than those membranes made in either Germany or Denmark. So we are at par with the other countries. India is not less than that. And only thing we need to develop a membrane processing facilities that will slowly come. We have all the major giants, those who are the membrane manufacturing giants are available in the country, and we are working with them. They will develop for us. We will only give the suggestions to them. We will give the R&D product to them, and they will develop and they will sell it to the companies.
Thank you, sir, indeed, for that very enlightening answer. And I think there are no more questions, and there is a lot of appreciation. Okay.
Sir, I have a question.
Yeah, please.
Good evening, sir. Sir, firstly, thank you for such a great and such an elaborate presentation. Sir, I was asking, like considering commercialization for, say, clarification of fruit juices. So, what technique can be most feasible and economical for membrane to avoid membrane fouling? Like, and even the cleaning protocols for membrane is very tedious. So, for commercialization, what technique can be used that can be feasible for industry purpose?
It's very simple. You have a very simple question, and I have a very simple answer. You can use ultrafiltration for clarification. Okay.
Sir, if you are using...
Yeah?
Sir, if you are using ultrafiltration as the separation process, membrane separation process?
No, clarification also it can be used, because you need to clear that sometimes it is required to clear the pectin. Or it is sometimes the unwanted material, the suspended material. And there are different ultrafiltration membranes based on the different cutoffs. That you have to decide which cutoff you want to use, which fruit juice you want to clear. And people are using for the clarification. Wine manufacturing, beer manufacturing, anywhere people are using. You don't have to use centrifuge for this.
Sir, like I was asking, membrane fouling occurs when we use any membrane.
Pardon?
So how membrane fouling occurs, right? When we use any membrane.
Yeah.
So how that can be avoided? Like for lab scale, we can use some acid alkali or some cleaning protocol. But for industry purpose, what can be a feasible technique?
Yeah, I think you missed the point. The membrane fouling can never be avoided. It's only concentration polarization which can be reversed. And membrane fouling, if it is fouls, then we need to change the membrane. And it's only the concentration polarization. You have a different strategies. You can reverse the flow. You can use the ultrasound. You can have some kind of a vibration, stop the flow, change the membrane, clean the membrane, put it back again. There are several strategies we can adopt. And we can have 2 units. One is working, another is cleaning.
Okay, okay, sir. Thank you.
Any other thing?
No, sir.
Thank you, Sakshi, for the question, and thank you, sir, for the answer. Sir, actually, I had one doubt. There was one term which was mentioned in your presentation, which was temperature polarization. So
Yes.
we have heard of concentration polarization. However, temperature polarization was a new term to me. So could you please?
No, because see, it is almost same now. When there is a temperature here, that will also lead to the increased osmotic pressure. So that also it is very similar to the concentration polarization. Concentration increases that because the imbalance between the difference in the osmotic pressure lead to the polarization.
Okay.
What polarization is? Imbalance between the what you call it is between the two draws, whether it is a draw solution or the feed solution, imbalance between the driving force, and it can be created by either by the temperature difference or by the concentration difference. Almost it is same in that case. If you increase the temperature, your osmotic pressure will increase. That in turn will affect your polarization.
Okay. Thank you, sir.
There is one question from Mr. Dhananjay Pandey, Dhananjay Sharma,
Okay,
also
sir.
from Desh Pandey. You can read, or
Yes.
they can ask themselves.
Okay.
Mr.
So-
Sharma.
हाँ हृदय जी आइए.
Sir, what is the status of milk processing using membranes in India?
I think many people are started using. The lot of R&D work is gone into in that direction. In this, actually, we are not doing is. It is done by the NCL Pune is in the forefront in using the membrane for the milk processing, and then in that they can concentrate milk up to 25 to 30 degree concentration, and that milk can be used to produce either the condensed milk or spray dried milk, because just fresh milk is not used for the concentrated milk or the spray dried milk. We need to concentrate around 30 degree Brix. So we need to do it, and then lot of work has been done by the people at the NCL, and those people have done industry aspects. I'm not sure which one is using, and maybe we have a very big plants coming up in India also, and maybe that they will start using when the technology is successful, people will be using it.
I think Dr. Hridesh Pandey has also commented something. Dr. Pandey, Hridesh, are you there?
Yes, sir. I just commented that commercially here at Amul, they are carrying out concentration of whey milk powder using this membrane processing.
Okay, thank you, Hridesh.
Yeah, it was only supporting you, sir.
No, thank you, Hridesh. That's what I'm saying. Thank you very much.
To support that membrane, it is being used commercially at Amul.
Yeah, exactly. That was
That
input was required.
Hridesh lives in Anand, so he knows, eh?
Yes, sir.
Good. Good. Lot of interactions, because this was really such a wide and elaborate presentation. So many ideas and concepts got clear today. We learned a lot by your presentation. Yes, Anas. So if there is no more questions, we can have the concluding remarks.
Sure. So I would now like to invite.
Before you say processing, would you, Professor Gajendra Singh, sir?
No, I don't have anything. I thank thank Navin for a very good presentation. I still have that question which I raised, No,
sir, I want to talk to you about this.
Sir.
The recent meeting, probably in the NAS meeting will take place next month.
Okay.
If you are available, I would like to have an elaborate discussion on this.
You have given
And I thank Dr. N Mishra for this series of webinars, very important, very relevant. Thank you, Mishra.
Sir, there's a lot of question. People say that we want mineral water and we are removing minerals.
Yes.
that was a very
My
relevant question.
other problem is in these systems, so much water is wasted.
Yes, sir.
And if we can concentrate and take some of the minerals out, I think it will be useful from the big plants at least.
Sure, sir.
Yeah,
Actually,
so-
maybe if you allow, we can work something more.
even in the fruit juice concentration, when you are doing, then some of the retentate can also be used as a mineral water, that is organic water.
Yes, sir.
After the concentration, when you are taking the water out, that will be a good source for making
That
the water.
is a potable water, in fact.
It's biological water, bio water.
Yes.
That is-
Maybe, sir.
Okay. Thank you.
Dr. Singh, I have a request.
Yes.
Sir, actually, people are confused about mineral water and removing the minerals from the water. If NAS can put their hands and then bring out a book, like you were bringing lot of booklets on Indian agriculture and all, if something can be brought on the Indian water, and like because people are selling the mineral water and we are removing the minerals from the water.
लेकिन रस्तोगी जी, even जो मिनरल वाटर कई कंपनी दे आर मेकिंग मिनरल वाटर really how many of them, barring only a few companies, most of them just they are telling the.
Yes, exactly, sir.
But I don't think they are adding minerals from
They are
outside.
not adding. So if something NAS can bring out some booklet on that, a small booklet, 2 pages, 3 pages, and circulate this, it will be a great addition, sir. It will clear many, because for the people, those who are not in the business here, they will have a very good understanding about this water.
Right.
So maybe please allow us to do something like that. Maybe if this is the meeting taking place this month, next month, sometime in June.
Yeah, 4th and 5th June.
Yes, sir, 4th June. Yeah, NAS. Maybe I look forward to meeting you and discussing this in depth, sir.
Okay, okay.
And
Okay, sir.
Yes,
Thank
sir,
you.
Thank you very much, sir.
So Anas will.
Yes, sir. So now I would like to invite Ms. Sakshi Gupta for a formal vote of thanks. Sakshi, just a minute, we are sharing the slide and then you can start.
Okay, sir. So shall I start?
Yes, you can start.
Good evening to Rastogi sir, Mishra sir, my dear seniors and juniors. It gives me immense pleasure to propose vote of thanks for our 38th lecture of FCTL webinar series. I wholeheartedly thank our speaker, Dr. Navin Kumar Rastogi sir, for sharing vast knowledge from scratch, like he started from membrane separation, its advantages as a non-thermal technology, factors affecting its performance, its various applications in the food industry, then coming on to forward osmosis, its techniques, how anthocyanin can be concentrated using the same like forward osmosis, and lastly concluding with the water purification hydration bag. Like he shared all this knowledge with such immense patience. I express my heartfelt gratitude to our mentor and coordinator, Professor N Mishra sir, for providing us this opportunity to gather like so much knowledge in areas of expertise of various seniors across the world, especially such great experts like Rastogi sir, with the help of this webinar series platform. Finally, a big thanks to audience and all the seniors who found out time and participated enthusiastically in this webinar series and graced this session with their valuable presence. We expect similar, in fact, more and more responses for our more upcoming webinar lectures. In the end, once again, thank you everyone who directly or indirectly participated and gave their presence for the success of this webinar. Thank you so much.
Okay, thank you, Rastogi ji.
Thank you, sir, for giving me this opportunity.